This week we're going to wrap up our GFS map by adding the calculated parameter vorticity. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. If you'll remember, last week we got some data from the GFS, and we used declarative plotting to make this geopotential heights map. Now, declarative plotting is great because in a few lines it lets us do a really pretty nice plot. But we wanted to show off some more of MetPy's new features, including the ability to do calculus correctly on a sphere. And this is something that is not necessarily the most straightforward thing, and the development team put a lot of time into it so you can get accurate calculations of things like divergence or vorticity. So I want to do the vorticity calculation and show you just how simple it is now that this is all implemented, and when using X-array, we don't even have to pass coordinate information to the calculation. So on my data set, I'm going to calculate vorticity. I'm going to store it in a variable called vorticity. mpcalc.vorticity, which means we're going to need to import metpy.calculations. So import metpy.calc as mpcalc. And now we should have help. If we do Shift Tab, we can look at the function signature. See, we take UV and some other parameters. Though if we go down and look, we notice that things like lat, lon, and coordinate reference system are optional if the X-array data array is used, which we have one, so we're going to use it. So I'm going to use my data set U component of wind isobaric, V component of wind isobaric. And with just that, we can calculate vorticity and see that it's now here available as a data variable. And it's got time 1, isobaric, lat, and lon as our coordinates. So we've now calculated vorticity over the domain of the model and at all of the isobaric levels that are available. Now we just want to have vorticity at one level, the 850 hectopascal level, so we can reproduce our plot. So let's go ahead and copy the elements of our plot. First we have our contour plot. Remember, we create the plots, then we put the plots on a map, and then we put the map in a container. So this does the contour plot, but now we need to make our raster plot of vorticity. We're going to use raster plot instead of image plot. It is a little bit more appropriate as we don't necessarily have rectangular bounds on this data. And image plot actually does have an issue with 0 to 360 coordinates right now, and that's something that the development team is looking at, but raster plot really is the more appropriate tool. I'm going to call it vorticity, VOR. I'm going to create an instance of raster plot, which means I need to import that. We haven't used that before on a MetPy Monday or in this notebook. So I'm going to import raster plot. We'll create the instance. We'll use our data set DS. Oh, not contour, but vorticity.field is vorticity. The level is the 850 hectopascal level. And let's start off right there. Oh, and units dot hectopascals. Our map panel is going to be almost identical. So we'll copy that down, except now we're going to have our vorticity plot as well. And our panel container is going to be identical because we still just have one map panel. So if we plot that, well, the plot we get's not really all that exciting. And that's because we need to limit the range of what's being colored here. And we also are going to scale it because we normally look at a scaled vorticity. So first, let's try the scaling. 1 times 10 to the 5th. Let's just rerun that. And we get scaled, but the same color. So now we need to set a range on our image, which we do with the image range attribute. And I'm going to set it from -10 to 10. And now we see something that looks a little bit more like what we would expect. We've got some contrast here. This is just the half degree, so it's a little bit blocky. But in these lows, we see vorticity maxima, as we would expect. We can make our map look a little bit more like what we might be used to seeing as well by changing the color map to something like the cool warm color map. And again, remember you have to rerun all of these cells when you're using the declarative, or put it all in one cell. And you'll notice that my color map didn't change. This is another tricky thing about using the declarative plotting interface, is you can set attributes that aren't there. It's color map. We don't get an error, it just doesn't modify the plot any. Now that we set that correctly, we get the nice colored vorticity map, more like what we're used to seeing. So though this really is just a one-line calculation, there's a lot of work that's gone in behind the scenes to get the calculus correct on a sphere and to make it this easy to ingest GFS data, select variables, do calculations, and plot it all without ever really having to work with or worry about the coordinate system. I hope that you found this useful, and I encourage you to modify this. Go out and try some of the other calculations. Try making multi-panel maps. This is a great tool for exploration, teaching, weather briefings, and more. I'll see you on next week's MetPy Monday.